Okay, so let's see. Radioactive decay. I'll show up in a second on the screen. Radioactive decay, second kind, is beta decay. We covered alpha decay last time. It's a situation where typically a heavy nucleus becomes something different and in the process emits an alpha particle, which we saw as a helium-4 nucleus. Helium-4 nuclei are super tightly bound up. They're really solid little nuclei. So those four particles together really act as a single particle a lot in nuclear physics. Beta decay in some ways is the same. It's a situation where you have a nucleus, let's say in this case carbon-14. Right? Standard carbon, carbon-12, 6 protons, 6 neutrons. Carbon-14, 6 protons, 8 neutrons. Turns out carbon-14 now, it's a lot lighter. It's a smaller thing than uranium-238, but it's also unstable. It becomes something else after a while. It doesn't remain carbon. It returns into another element altogether. And another thing that's similar about alpha decay is when it does so, it produces other particles. Okay, one of them is a beta particle. Okay, so it was discovered that carbon-14, after a little while, became nitrogen-14. Now, nitrogen, as you may know, has 7 protons. So look, we've added a proton. Isn't that weird? Okay, added a proton. And also other things are produced. Now the other things that are produced in this case is an electron plus something known as a neutrino. Okay. Actually, you'll see in the textbook it's got a bar over it. It's actually what's known as an anti-neutrino. How do you like that? So not only does carbon become nitrogen, it also emits a couple other particles. One is an electron. Historically, the electron it was not known that it was an electron that was being produced by radioactivity. They call it a beta particle. So a lot of times you'll see it written beta instead of electron. In fact, beta minus is what you'll see a lot. Okay. There's actually 2 kinds of beta decay. There's this one here, beta minus decay. Okay. Because it produces a negative beta particle. Okay. Beta minus. So we have a carbon becoming a nitrogen, but producing an electron and a neutrino. Now, 3 things I want to say about this. Number 1 is that you have to see that what happens here is that it maintains the same number of overall particles. Carbon-14 and nitrogen-14 both have 14 nucleons inside of them. Okay. But a nitrogen has 1 more proton. So what obviously had to happen here is that a neutron actually turned into a proton. That can happen in beta decay. It does not happen in alpha decay, but it happens here. A neutron here actually turns into a proton inside the nucleus and produces an electron and a neutrino. That's the first thing to know. First thing to notice is that a neutron actually becomes a proton. It turns out that if you have a bare neutron, like all by itself, it will actually become a proton. It won't stay by itself. Okay, an isolated neutron will not last more than an average of about 11 minutes before it becomes a proton and an electron and a neutrino. The electron is just a plain old standard issue electron that gets produced by this decay. Neutrino is a really interesting little particle. They're all over the place. They're all burning right through your body right now, coming mostly from the sun, and are completely swarming us all the time, but they don't interact with us very much. Okay. But they're ghostly little particles that were first predicted back in, let me check the date here, predicted in 1930 to exist and were discovered in 1956, and now neutrino physics is a booming business. So neutrinos are produced. They are small, they are neutral, okay, and really hard to detect, it turns out. So the neutron turns into a proton and stays inside the nucleus, but it also, along the way, becomes, so the neutron becomes a proton plus an electron plus neutrino. Okay, so this is what's really happening. Okay. But the neutron inside carbon stays inside the nucleus, becoming a proton, making it nitrogen, and the electron and the neutrino disappear. They take on off. Neutrino goes off, Lord knows where. Electron will go a little ways before it interacts with something else. Okay. But this is the reaction that's happening within the reaction. This is happening inside the nucleus. One of the neutrons becomes a proton. Okay. And an electron and a neutrino. Notice that the charge is the same. The charge on the left-hand side of this circled equation here is 0. It's a neutron. On the right-hand side, we have a proton. This actually should be P+. And an electron. So the net charge on the right-hand side is also 0. Okay, so we say that charge is conserved. Not only for this reaction in the circle, but for the larger reaction, right? On this side, we have a total positive charge of 6, right? 6 protons in the carbon. Over here, we have a total charge of 6 because we have 7 protons plus an electron. So 7 pluses minus an electron gives us also 6. In both cases, charge is conserved. So this reaction here is what's happening inside the carbon, okay? And so when the neutron turns into a proton inside the carbon becomes nitrogen. And this electron and neutrino here are the same as this electron and neutrino there. Okay, these are the same. This electron and that electron are the same. That neutrino and that neutrino are also the same. Okay. So in general, negative beta decay looks like this. You have X, A, Z becomes, let me find a different color here. The general expression for negative beta decay is X, AZ becomes a new nucleus, Y. A is the same, but we now have Z plus 1. We've added a proton. Lost a neutron, added a proton, plus the electron, plus the neutrino. Again, the bar over the neutrino really means anti-neutrino. That's not something we're going to get into right now. They're both neutrinos, so that's why I'm calling them that. So this is the general expression for beta minus decay, okay, or negative beta decay. Okay, in a similar way, we can have something called positive beta decay. Okay. An example of this is nitrogen 12. I'm going to have to change colors here. My favorite is this pink, but it's just getting so worn out. Will become carbon 12 plus a new particle. I don't think we've talked about this particle yet. Not E minus, but E plus. In other words, all the signs is different from up here. Okay, this is known as a beta, a positive beta particle. Can you read that? I'm going to erase that. This is known, there's two names for this. You can call this a beta positive, or you can call it a positron. A positron is the antiparticle of the electron. It's got the same mass, it's got all of the same properties as an electron except for its charge is positive. Think of it just like an electron but with a positive charge. It's an antiparticle. Antimatter is totally real. Doesn't sound real because of the way it's named, but it's totally real. It's made in labs all the time. Okay, you just can't keep it. It's hard to keep it around. That's the problem. I'll say more about that later. But this also produces a neutrino. So nitrogen 6. I'm sorry, that should be nitrogen 7, right? The 7 in here. I didn't put the 7 to carbon 6. So in this case, what's happening is we're going from some nucleus to a new nucleus. Again, A stays the same, but now we're going to Z minus 1. Charge is still conserved, plus a positron, plus a neutrino, not an antineutrino. This, let me actually put a different color box around this because the marker's getting a little weary. This is the general expression for positive beta decay. Okay. Same kind of thing happens in here. Inside this, there is in fact its own little reaction going on, right? The proton inside the nitrogen becomes a neutron plus the positron plus the neutrino. Okay. So this is all happening inside the nucleus. And again, this positron here is that positron, and that neutrino is that neutrino. Okay. The half-lives for these are interesting. For this one here, the half-life I think is 5,700 years. T1 half for this reaction, not reaction, decay really is correct, is about 5,700 years. Far shorter than uranium-238's 4.5 billion years. This one here has a half-life of only 11 milliseconds. So nitrogen-12 only remains nitrogen-12 for a handful of milliseconds. Carbon-14 remains carbon-14 for several thousand years on average before it turns into something else. So half-lives, 11 milliseconds, 5,700 years, 4.5 billion years, and there's also half-lives way shorter than this. So half-lives are all over the map. Okay. That's beta decay. Next up, gamma decay, and an example.